recording. I'm going to share my screen. So we're going to finish up that example from yesterday. Maybe you guys had an opportunity to finish that as well, okay? So we can double check our work here. So we had looked at that section 4.5, problem number 18, okay? Let me again make sure all this stuff is working, wonderful. All right, so now when we're looking at this problem, going through that curve sketching process, right, the beginning portion, even that can give us a lot of information. The more we practice, of course, the more graphing we do, we get a little bit more intuitive about recognizing these components. Okay, let's start off with number 18, page 321 of our book, y equals x over x cubed minus 1. Right, first up the domain, making sure we don't get a 0 in that denominator. Only happens when x equals 1. So we get that restricted value, or later a vertical asymptote, where we get that 0 in denominator. Domain, right, on either side of 1, we're defined everywhere. It's only at 1 itself, so that's what we kind of skip over. We have a gap in where our function is defined. So we go from negative infinity to 1, and then from 1 to infinity. Okay. The intercepts, again, algebra work here, just find out some specific points. In this case, it just turns out to be 1 point. We're crossing the y-axis when x equals 0. We're crossing the x-axis when y equals 0. They both turn out to be the same point, the origin 0, 0. So that was the only point where we're going to touch or cross that x-axis, y-axis, right? We only cross the y-axis once for any function. The x-axis we can cross multiple times possibly, but in this case, our work shows only cross once. Symmetry, I skip over that work. Okay. Asymptotes, so when we do have a vertical asymptote, a 0 in denominator, that doesn't cancel, right? Kind of going through our chapter 2 work, when we see 0 over 0, our function's undefined, but we might just have a hole in our graph, that removable discontinuity. But when it's a constant, a number over 0, like 1 over 0 in this case, we're going to get a vertical asymptote. Okay, our function approaches infinity, whether it be positive or negative infinity. That's when we do our kind of approach from the left, approach from the right, sign check kind of work. Working on those aspects we saw yesterday. We're approaching negative infinity from the left of 1, positive infinity from the right of 1. So with that information, and then of course, horizontal asymptote discussion, taking the limits at infinity, positive, negative, we can go through our work dividing by the highest power of x, or now L'Hopital's rule from section 4.4, taking our derivative numerator, derivative denominator, comparing those rates of change, and seeing again we get that 0, 1 over a really large value going to 0. So our horizontal asymptote, y equals 0, the x-axis. So just from that detail alone, I can already imagine the start of our graph, vertical asymptote at x equals 1, our only intercept at the origin 0, 0, approaching positive infinity from the right. As we go out towards positive infinity for the x values, x bigger and bigger, our y value getting closer and closer to the x-axis, y equals 0. We're never going to touch or cross beyond. Our only intercept was there. So I know I'm going to stay well above, well not well above, but I'm going to stay above completely the x-axis there. To the left of negative of 1, pardon me, right? That 1 with a little negative exponent. Approaching 1 from the left, we're going down to negative infinity. Okay, we have our intercept at the origin. Extending outwards towards negative infinity, where again we're going to get 0. I know I have to go through the x-axis here, and we start to see this kind of image playing out. I'm going to have to get closer and closer to 0, the x-axis, y equals 0, as x gets more and more negative. So now we have to figure out what's happening in between. Okay? Whew. All right, so now I expected to find a maximum and an inflection point in that space. So let's see with our derivatives if that comes to fruition, if that actually happens, as I suspect, or maybe something strange happens. Okay? All right, so with that said, I'm going to take this away. We'll come back to that diagram. So again, looking at That's section 4.5, our curve sketching. Let's look at that problem number 18. It was page 321, if I remember correctly. There we go. Y was equal to x over x cubed minus 1. Okay, slide that over, sorry. So with that function, we had done A through D yesterday. Let's start step E, looking at our intervals of increase and decrease. You can see as we go on, my notation gets lighter and lighter, lazier and lazier in what I want to write out. But now we're going to be using our derivative, right? So if y is equal to x over x cubed minus 1, our derivative, we're going to need the quotient rule, right? So the derivative of the numerator, derivative of x is 1, keeping the same denominator, x cubed minus 1, minus, right, our quotient rule, we have a subtraction. The original numerator, x times the derivative of the denominator, derivative of x cubed minus 1, derivative of x cubed, 3x squared. The constant, the minus 1, goes to 0. And that's all over our denominator squared, the original denominator. I cannot cancel here, right, with that subtraction. That x cubed minus 1 is kind of attached to these terms as well. So I can't just simply cancel that out. I'm going to want to distribute, combine like terms, if and where possible, to get our result here. Okay, so for my y prime, distributing that 1 through, x cubed minus 1, doing this multiplication, right, multiplying these two together, x times 3x squared, 3x squared, then making that negative, oh, x cubed, sorry, boom, boom, there we go, make sure I get my exponent work right. X the first times x squared, x cubed, there we go, better, because now we can actually combine some of those terms up in the numerator. This is still x cubed minus 1 squared. Combining x cubed minus 3x cubed, negative 2x cubed minus 1, all over that denominator squared. I can't cancel anything. Nothing simplifies. But there's our derivative. Double check my signs, my calculations, okay? So there's our first derivative. Later, for concavity, we're going to have to take the derivative of that. Okay. But let's start to work on this. So then in this case, finding our critical numbers, right, where that derivative equals 0. We're still going to be undefined. Let me put over here, right, that 0 in denominator is still going to be the same, right, at x equals 1. When we get a 0 in denominator, that vertical asymptote, definitely something strange happening there. Okay, but focusing on this one, I'll move this up. Focusing on that y prime equals 0, taking our derivative, negative 2x cubed minus 1 over x cubed minus 1 squared, setting that equal to 0. Multiplying both sides by that denominator, or just recognizing that that rational expression is going to be 0 whenever the numerator is 0. Adding the 1 to both sides. Then we'll divide by the negative 2. And again, with a cube root, right, with our odd power there, we don't mind having a negative value. If we have an even power, x squared, x to the 4th, x to the 6th, we know that those can never be negative. But odd powers, odd degrees, they can have a negative result. So just finish these up, taking our cube root on both sides. We get, again, this kind of strange value, the cube root of -1/2. Okay? And while I'm here, let me grab my calculator. So of course, right, otherwise we just kind of estimate, we'd make it up. If I have this -1/2 raised to the 1/3 power, taking a cube root, this is approximately -0.7937, okay? Just doing that calculation briefly, a cube root, okay? But just getting that location, that's that x coordinate. So then when we start to look at our intervals of increase and decrease, we had those key points, those critical numbers at the cube root -1/2, right? That -0.7937, and also at 1, right? So our derivative, let's see what color I want to use, green, I guess, y prime, my derivative, it was 0 here. I'm going to say it's undefined, right? Where we have that vertical asymptote at 1. But we still want to think about what's happening on either side to, again, influence us to describe what's happening in that function, that graph. So choosing some test values, something smaller than the cube root of -1/2, something smaller than -0.7937. We can do like -2, -1, probably a little bit easier. Between our critical number and that vertical asymptote, 0 is always good. And then something bigger than 1, +2 there. All right, so there's our test value. So when I look at our derivative, y prime was -2 x cubed minus 1 over the x cubed minus 1 squared. I'm going to slide this up. Taking that expression, that denominator, because of the squaring, that's going to be positive no matter what. Any x we plug in, because we'll calculate inside the brackets, inside parentheses if you use those instead, and square after, that's always going to be positive. So the real concern is what's happening up in that numerator. Unfortunately, I can't really factor it nicely, but with these values, right, it's not going to be too difficult to compute. So plugging in x is -2. Watching our signs here, this denominator, I know that's going to be positive in the end, okay? But plugging in that -2, this becomes -2 times -2 cubed, -8 minus 1 over that positive quantity. And then looking at that positive denominator, numerator, -2 times -8, positive 16 minus 1, that's going to be positive as well. So in the end, over here, we're positive, we're going to be increasing in that space. Then at x equals 0, again, the denominator I know is always going to be positive, so I don't even bother computing that, but you can if you wish. Computing here, right? 0 cubed, still 0 times 0, that's just going to zero that term out, minus 1 over the positive. So this becomes negative over positive, which is, of course, negative, right? And so exactly as some of those other components about our horizontal asymptote, our intercepts, or now singular intercept, right? That behavior kind of informed me that I was going to get a maximum, right? We're increasing and decreasing. on this side of 0 showing up, right? Because we're increasing, dropping back down to go to negative infinity as we approach that vertical asymptote, okay? So this side we're going downwards to negative infinity. At positive 2, we hopefully understand what's going to happen there. As I go from left to right, we're going to see that we're going to be decreasing again, right? We're going to go from positive infinity down. So we should hopefully, as I compute this, see that when I plug in positive 2, and let me not forget my cube, negative 2 times 2 cubed 8, negative 2 times positive 8, right? Minus that 1 over the positive, and let's go to here, positive in the numerator, negative minus 1, still negative, and negative, positive, negative, right? Watch that calculation. Oh, sorry. There we go, better. Sorry about that. So plugging in x is positive 2, negative 2, 2 cubed is positive 8, negative 2 times positive 8, negative 16, minus 1, still negative. Denominator, like we've been working on, positive all the way across, and negative or positive is negative. So then, up here, we're negative, we're decreasing on that side. So then for our intervals of decrease and increase, we can say here that equation, y is increasing on just one interval, right? Working from left to right, it's only increasing from negative infinity to negative, our critical number, sorry, the cube root of negative 1/2 or negative cube root of 1/2, that would work as well. We go up to our critical number, not our test value, not that test value I plugged in. And then y is decreasing on these intervals from that critical number up to 1, where the vertical asymptote was, our other semi-critical number, and then also from 1 to infinity. Okay, now again, I know it's kind of small here. Okay. Let's see here. Exactly. So looking at that graph, we're not going to get that local minimum because we go negative, and then on the other side, there's that vertical asymptote here. Then it starts off negative again, sweeping down, always working lower. So it's not going to have any local minimums because we don't have a change from negative to positive, from decreasing to increasing. The only thing we're going to get is this local maximum at that critical number we located. Exactly, right? So since we don't have that nice change from decreasing to increase, we're not going to get a minimum at all. So for part, that was E, so part F, our max and min, that first derivative test, we're going to have a local max when x equals that cube root of negative 1/2, that critical number where we change from increasing to decreasing. There's going to be no local minimums. Okay, and again, we know it's only local because with our work with the vertical asymptote earlier, we saw that our graph was going to positive infinity on one side, negative infinity on the other side, right? So definitely there's going to be y values higher that we could locate on that equation, on that curve. Okay, and then while we have it, if that's my x value, my y is going to be that x over x cubed minus 1. So plugging in that value for x, again, it's going to be some weird decimal number. Cube root, sorry. Cubed minus 1. Okay, So we're going to get for this y value, I know it's a little bit, a lot, not just a little bit, congested here. Negative cube root of, or the cube root of negative 1/2 cubed, negative 1/2 minus 1. I'll put a little dot, dot, dot here. So that maximum is going to occur. There's my x coordinate. Working on this a little bit, we'd end up with this coordinate, and you can double check that this should be here. That's but again, that's just some messy algebra, messy arithmetic, plugging numbers in. And the cube root is going to be negative with that negative, so it's going to be a positive y value in the end. All right. But it is just kind of this strange quantity, which I probably wouldn't necessarily worry about getting a decimal value for, or even knowing exactly where that is. We're just going to kind of generically place that on our graph when it comes to building up. But again, no local mins. We get that value, the big part here, that increasing, decreasing discussion. And so then this last big time consuming part, G, our discussion with concavity, right? That second derivative. So for our second derivative, we're going to need to use that quotient rule again. In that denominator is going to be a chain rule when we evaluate, right? So if we need to, my f, my numerator, negative 2, x cubed minus 1, its derivative, negative 6x squared. My denominator, that binomial squared. Derivative here, chain rule. The outer function, the fact that we were squaring. Then our inner function, 3x squared. Like so. Move this up. Okay. Like that. Slide this down if I can. Better, okay. That much better. But then when I start to work on this 2, 3x squared I can bring together first. Just think about this distribution, 6x squared, q minus 1 to the first power, g prime, 6x to the 5th minus 6x squared. Definitely kind of messy here. But let's hope, fingers crossed, that this calculation for our inflection point will somewhat clean up nicely. Right, so we're going to get that denominator squared. So it's going to be that x cubed minus 1 squared squared. So that's going to be to the 4th power. I'm sorry. In the numerator, derivative of the numerator, negative 6x squared times denominator minus numerator times denominator squared. I know I'm going to have to squeeze that right here. Okay. And maybe leave it in that form could have been helpful. So let me do that right here. I'll move this up. But what I have that negative 6x squared times this x cubed minus 1 squared. I don't know we're redundant with our brackets and so on, but leave it like that for now. Minus that green negative 2x cubed minus 1. And then this one, let me actually rewrite it as that 6x squared times x cubed minus 1 for a second. Oh, sorry, wrong color. And that's all over that x cubed minus 1 raised to the 4th power. I'm playing around with my notation a little bit. Because now as I start to look at these, just in the hopes of trying to simplify, because we're going to have to set this equal to 0 to get our possible inflection point right, what I start to see is that they share the 6x squared. They share at least one x cubed minus 1. So in that case, if I factor out those components, what's going to be left? If I factor that out, this was an x cubed minus 1 squared, so there's still an x cubed minus 1 to the 1st power there, and also my negative. Let's not forget that negative sign. Okay? And again, I'll probably bring in that negative and work with that as we go along. Minus, I still have this negative 2x cubed minus 1. But like I said, if I factor out the 6x squared, the x cubed minus 1, if I factor that out, all that's left over is, if you will, a 1 there, a placeholder for a second. Simplifying our algebra here. You could FOIL everything out, combine like terms, work it that way. All right, but let's see how this works for us. All right. So with that said, let me do a little bit of work. We're going to be able to simplify a little bit up here in just a minute. But at least in those brackets, let me do some of that work. Okay, and again, I know, as I mentioned before, these problems do get very time-consuming with all this algebra that we're doing. But let's start to manage this out. Okay, so distributing this negative in, minus x cubed, negative negative makes that a plus 1. Working on this, right? The negative coming in makes these both positives. Multiplying by 1, so we get a plus 2x cubed plus 1. Okay. Leave that there. Working on that. 6x squared, x cubed minus 1. In these brackets, negative x cubed plus 2x squared, 2x cubed, pardon me. We got a positive x cubed. 1 plus 1, 2. That denominator has held steady for us. But now, what can help? This x cubed minus 1 can cancel with one of these. That drops it down to an x cubed minus 1 cubed. I can't do anything with the 6x squared up front. So now for my second derivative, at least, 6x squared times x cubed plus 2 now, all over this x cubed minus 1 cubed. Okay. So now with that second derivative, our concavity discussion comes in, our possible inflection points. Where our second derivative is 0, or possibly undefined. Okay, but again, this is going to be 0 in denominator, and that happens when x equals 1, where we have that vertical asymptote, right? So again, that vertical asymptote component is going to be a place where maybe that concavity can change from being concave up to concave down or vice versa. So it might not necessarily be a point, but a kind of location where that concavity changes. But definitely that second derivative equals 0. That's going to be the one that's going to take some action. Okay. Cross multiplying both sides by LCD. Again, we focus on where that second derivative equals 0. Okay. Where does that happen? When x equals 0. Something interesting happening there. But also x cubed plus 2 equals 0. Don't mind me jumping to it. That's going to be x equals the cube root of negative 2. Right? Or likewise, the negative of the cube root of 2. And if you want to get a decimal, we can. Let's do that real quick. 2 to the 1/3 power. The cube root of 2. Negative 1.26, right? It's 1.2599, but negative, so I can round like so. Okay. So when I start to look at our number line here, and I know it's a little bit jammed here, that second derivative, our critical values, right, are those locations of our possible inflection points. I know I get lazy and call it critical numbers sometimes here. Our second derivative is 0 here, 0 here, undefined, right? We can get that vertical asymptote. But let's take some test values on either side. So something less than the cube root of negative 2, something less than negative 1.26, right? Negative 2. Something between negative 2 under that cube root, the negative of the cube root of 2. We do negative 1, right? Something between 0 and 1, 1/2, bigger than 1, positive 2, let's say. So as we start to compute, looking at our second derivative, and this one's a little bit more in depth, unfortunately. We can't make as many shortcuts. That 6x squared, that part at least is always positive, but these others we're going to have to check because that x cubed, that entire quantity cubed, it does have the possibility of alternating from positive to negative, so on. So we're going to start to take our values, okay? So when x equals negative 2, let's see if we can't reason this out. Okay. So as I start to evaluate, move this out of the way. I know a lot going on here. Try to zoom in. All right, so taking this component, right, that squared, like I mentioned before, positive. Negative 2 cubed, negative 8 plus 2, still negative. Negative 2 cubed, negative 8 minus 1, negative. Negative or negative makes positive, right? We're going to be concave up. In that region. Okay. With x equals -1, plugging that in, what are we going to get here? Up front, positive with that x squared, -1 cubed, -1 plus 2, positive, -1 cubed, -1 minus 1, -2, negative. Positive or negative makes negative. We're going to be concave down in that region. Okay. Then finishing out these other values. And so at 0, we saw another place where our second derivative became 0. So we just have to see that, check if we're going to change concavity at that point. Let's see here, right? So if we plug in that 1/2, positive, that test value, right? Looking at that, positive. Positive cubed, positive plus 2 stays positive. 1/2 cubed, 1/8, 1/8 minus 1, negative. Positive or negative makes negative. So we're still going to be concave down in this space, opening downwards in that region. It just gets to the point where our second derivative happens to be 0 as well. The last test value at +2, right? Again, with our graphing earlier, we might suspect what's going to happen there. But just to be careful, we'll do that work. That's squared, positive, 2 cubed, positive plus 2, positive. Okay. Quick. 2 cubed, 8 minus 1, positive. All positive stays positive, right? So we're going to be concave up in that space. All right. I know, kind of tedious there. You could also plug into a calculator, but imagine you're doing this without a calculator, right? Just watch out that order operations. So getting all those different intervals with our different test values, okay, we start to identify then that for that graph, for that equation, we're going to be concave up, right, for those two intervals. Let's one more time. There we go. To the left of that cube root of -2 and to the right of +1. we're going to be concave down. From here, that cube root of -2 or negative cube root of 2 is fine as well. And at this point, we can either, since we're staying concave down the entire time, go from -2 underneath that cube root up to 1, or we can separate, right? I know sometimes with those increasing, decreasing, I kind of mentioned separating out the concavity, right? Maybe a similar aspect, but not as big of a deal. But I'll do it like so. And again, that's just a matter of seeing how I gotten that 0 here at x equals 0. So just separating like so. So there's our intervals of concavity. The only time we actually change concavity from being concave up to concave down, that is in a vertical asymptote, we can get a point there at that cube root of -2. Okay, so over here, for our inflection point, at that cube root of -2, if we were to go back into our original equation, that's going to be -2 minus 1. We're going to get this coordinate. That should be a -3. So that's going to be a negative up front. But again, negative is going to turn to a positive. Okay. But again, that inflection point, messy because of our strange value. But again, a real life problem because most often we're not going to get nice, simple, rational integer values. We try to build them that way, but it's not guaranteed, especially once that second derivative comes around. It does get pretty messy many times over. But there's our inflection point. So putting that together with our increasing, decreasing, concavity intervals now, this inflection point, and those asymptotes we had talked about earlier, yesterday I should say. When it comes into part H then, our sketching of the graph, when we start to put in that detail, we knew at the origin we're going to pass through at 1, we get that vertical asymptote. Okay, I'm going to slide this up. Now plugging in some of our other important information that we just gathered, taking us that time, right? With our intervals of increase and decrease. We have that critical number at x was the cube root of -1/2, right? That -0.79, right? Roughly -0.8 if you rounded. The y coordinate up here, whatever that decimal value may be. So if I start to put in that critical number, probably down a little bit further, but that's all right. That cube root of -1/2, our y coordinate, that maximum. And then, right, so that was this part. We're going to be increasing, starting lower, climbing up, getting that maximum, then dropping downwards, decreasing. Then on this side, we're decreasing as well. Before I forget to put it up there, we also had that horizontal asymptote that we can cross if necessary. But we see we only cross it once at the origin. That inflection point, finally, what I was getting towards with our concavity. Where did I put that? There it is. Yep. Oh, there it is. Okay, good. I don't lose those notes. All right. So then our inflection point, the x coordinate, where that concavity changes, negative 2 underneath that cube root. The y coordinate, we're going to be, let's say, right about here. Okay. So there's my inflection point. Here's my local maximum, our intercept. So as we start to build up our graph, right, we're going to approach the horizontal asymptote, get closer and closer, increasing, right? My graph's going upwards. At this point, I know the arc doesn't look as strong, but we're going to be concave up in that space. But now at that inflection point, now I'm going to switch to being concave down. So now I imagine kind of more so arcing where our graph's going downwards, opening downwards, still increasing to get to that maximum, dropping down across through the origin, our x and y intercept, still decreasing, concave down, heading towards negative infinity as x approaches 1 from the left. All right, so there's our increasing to the maximum, decreasing, falling away, concave up, now switching to concave down. On this side of 1, approaching pos infinity, going left, right, decreasing downwards, getting closer and closer to that horizontal asymptote, staying concave up, like so. So there's our graph, just like we had kind of pictured and drawn in yesterday. Now with our first derivative, second derivative, we're able to locate that maximum, that inflection point, see those particular locations, though they are kind of these weird cubic values, cube root of -1/2, cube root of -2, at least we can definitely identify them. Okay? All right. Definitely a long time to get through this problem because of the messier quotient rule, right? But at least we can see how those details can give us a clue on what that graph's going to look like. Okay? Reinforce what we kind of think about, giving us that more formal background and understanding. Some of those steps we would have taken probably back with pre-calculus and whatnot. But this also gives us a way of finding those maximums and inflection points that maybe pre-calculus skills wouldn't have given us. Okay? All right. So with that said, I'll leave it at that. You can see I'm in my office. So I'm going to try to find those other examples I had written up before for other classes so I can post those for you guys today. Okay? And so again, this weekend, definitely getting that practice with our curve sketching, going through those skills. I'll try to find some functions. I'll make up I think I'll try to find that review sheet, practice sheet for chapter 4 as well to give you guys some glimpse there, right? We don't have that much more time in the course and the semester remaining. All right, so we have to get to optimization, and I want to introduce chapter 5 for us in the coming week, okay? All right, so thank you very much, everybody. If you have any questions, let me know. Otherwise, take care, be safe out there. See y'all soon. All right, there we go. Thank you, guys. There we go. Stop sharing. Stop recording.